start this chapter, we need to talk about another phase of matter that we talked about at the beginning of the semester, which is what is a gas. So as we learned in that first chapter, gases are one of our phases of matter. Gases are composed of molecules that move randomly and very quickly inside this container. And in this chapter, we're going to look at how we make measurements of gases and utilize them in chemical reactions. In terms of practical applications, you probably understand what a gas is, right? Like I'm breathing in air right now. That air is an example of a gas. What we'll be looking at this chapter, though, is how to make measurements about that gas. Like, how do I know how many molecules are in the air that I'm breathing? If I want, and maybe I need to know that because I want to use some air from the room, put it in a container where I'm going to have a reaction that uses up something in the air. Like, for example, there's oxygen in the air. Maybe I'm going to do a reaction in a closed container that uses up some of that oxygen. I need to know how many moles of oxygen were in whatever air sample I calculated. And we'll look at how to figure that out in this chapter. So we're also going to be able to talk about some of the properties of a gas. How do I talk about gases? What are different properties affecting them? So let's take a look at that. There we go. So first off, we'll have the idea of pressure. So at any point in time, as long as you're on the Earth, and none of us are astronauts, so we're not in space, anywhere I'm at on the Earth, there is atmosphere on top of me in the sense there's air, and it is literally colliding with me and applying pressure. That's what we feel, and it's called atmospheric pressure. So the atmospheric pressure is how much force is being put down on me by the fact that there are a bunch of air molecules on top of me. And so this can be measured with different types of information, like we can measure this at different places, and that's going to affect the properties of gas molecules. For example, gas behaves differently where I'm at right now, which is pretty close to sea level, versus if you compare if I go to Colorado in an area that's in the mountains, there's going to be a different amount of air on top of us, and that's going to change the properties of those gas molecules. They'll only change it some, like it still is breathable, for example, but if you have difficulty breathing, actually, if you go to Colorado, it can be hard to breathe when you go outside. And that's because in that space, there's actually less oxygen atoms, or less oxygen molecules in the air. Because as you go to higher elevations, we'll look at some calculations later, you're actually going to have fewer molecules per unit volume. So if you're used to breathing air at sea level, it's going to feel differently if you go to somewhere up high. Now, let's talk about all those properties now. So first, we have the concept of pressure. I've used this word a few times, so what does it mean? Pressure is defined as the force exerted on a given area. So for example, the air that is on top of me that pushes down. It applies across an area, the surface of me, Dr. Leslie. So the pressure, where this comes from, is because those gas molecules are moving around, and they exert a force when they collide with us. So molecules are literally running into you right now. Having said that, they're not running into you with so much force that you have a problem, right? Like I can walk through a room and I don't go, oh my gosh, I'm so tired. The gas molecules just keep hitting me, right? That doesn't happen. But we do feel some force from that. We feel some resistance from that movement, whereas I would feel differently if I were to try to walk on the moon. There are other problems there, like gravity's different, that's going to feel different. But there'll be fewer there, but it doesn't have a bunch of air trapped there because it doesn't have an atmosphere, so it doesn't have a bunch of molecules for me to run into, so that's going to be a different property, in addition to the whole gravity thing. So, I do want to mention that there's the English system uses a unit for pressure called pounds per square inch. We're not going to talk about this, but I mention it because it's one of the most likely places you've encountered pressure. Your tire that you use if you've got a car or a bike or any of those things, anything with a tire, is you have molecules in it that cause it to have the right shape and to be good for riding on the road, and the amount of molecules inside that tire, in addition to its volume, control how much pressure is being applied by the molecules inside the tire, and you can measure that because there's a difference. There are more molecules inside the tire than the amount outside the tire, assuming you don't have a completely flat tire. As long as your tire's not flat, there are more molecules inside than outside. And that leads to a higher pressure. There's more force. As those molecules collide with the walls of the tire, they push it outwards. And that's what causes some of the properties of your tire. So for this class, rather than pounds per square inch, though, we're primarily going to use the atmosphere and ATM as our unit of gas measurement. And this is, at sea level, you're going to on average feel 1 atmosphere, like the fact that there's 1 atmosphere on top of you. We're also going to use a unit called millimeters of mercury sometimes. And it has another name called Torr. These units actually have the same value. It's just they're thought of a bit differently because millimeters of mercury is specific to the instrument that was used to measure pressure in a lot of cases. So that's where this comes from. The idea of a millimeter of mercury is if I have a barometer that uses mercury, this is the amount of pressure that causes it to raise a certain amount up. Like you think of like with a thermometer when we mostly use alcohol thermometers nowadays, but when you see the bulb increase in size because of temperature, barometers are set up so it is the pressure colliding with it that causes the value to change. And so if you have a barometer that uses mercury, every millimeter of mercury of pressure would cause the barometer to increase in how far it goes by a millimeter. To be able to take this unit and then compare it to atmospheres, we know that 1 atmosphere is 760 millimeters of mercury. And I do want you to know this conversion factor. We'll use that a lot because a lot of our problems are going to be in atmospheres in terms of the constants we're using. So we have to convert them to that, but you may have a measurement millimeters of mercury, so you have to go back and forth. I also want you to know that a millimeter of mercury is the same thing as a torr, just torr is named after an individual instead. This also means that 1 atmosphere is equal to 760 torr. You can convert from any one of these units to the other two. And then, like I mentioned here, a mercury barometer is an example of a device that can be used for measuring atmospheric pressure, and that's where our millimeters of mercury unit comes from. Now, how does this thing actually work? Like, what's a barometer do? So the idea is we have this tube. So there's a picture here from your text 8.4, figure 8.4. But the idea is you've got a tube. It's sealed off on one end, and it's placed into some type of liquid. And inside this, at the top, inside the tube, there's going to be a vacuum. It's not like it's filled with air. It's not filled with anything. So what happens is outside, hey, we've got pressure because there are molecules above us. And there's pressure everywhere being exerted on the fluids that are inside the container that has the barometer. And what's going to happen is that inside the vacuum, no pressure in the vacuum. And the reason for that is because it's a vacuum, there aren't air molecules. We said pressure comes from force of the molecules colliding with the surface. If you have a vacuum, that's an absence of molecules. And like technically there's a handful of molecules in there, so we don't have a perfect vacuum, but we're going to treat it like a perfect vacuum for calculations, and practically it's pretty close to one of those. So since there aren't any molecules there, there's no pressure there. And what happens is based on the atmospheric pressure, how much pressure is being pushed onto this liquid, it's going to push the liquid up some distance. And so the distance is going to raise above the level of the liquid it's in. And this, if this were mercury, would be measured in millimeters of mercury. How many millimeters does it go up? The idea being that as it goes up the tube, it's having to fight the force of gravity, but the pressure is able to keep applying, and so it keeps going up until gravity balances out the pressure. Now, the reason mercury barometers are helpful is if you compare it to what it would take for water, water is less useful because it has to move further to counteract this pressure. The reason for that is water is significantly less dense. Mercury is one of the densest liquids on Earth, and so because it's very dense, every millimeter it moves is a significantly more larger amount of mass than a millimeter of water. And so because water is less dense, it doesn't take as much force to push it up the tube. And so I would have to have very, very tall barometers if I wanted to use water. So mercury does a better job at this, and so it's able to move a shorter distance, which is why it gets useful towards a barometer. Note that mercury has a bunch of health concerns, and so there are reasons we don't use these all the time and why this isn't the best material for stuff. It's why we quit using mercury thermometers for the most part, unless you have a specific application that requires one, because while mercury is really cool because it's a liquid metal, it also can like get into your skin and it does stuff and it's got some properties that are not good for us. So we have to be careful about interacting with mercury, so we only use it when we need to. That's why we don't have any mercury devices inside of our general chemistry laboratories. So, with this, the height it raises tells us how much pressure was being exerted on it. So if you were to move this barometer to a new location, like take it from Dr. Leslie's house, which is pretty close to sea level, and I were to take it to Colorado up on a mountain, or even in Georgia, let's say we go on top of Pine Mountain or something. I don't actually know how tall Pine Mountain is, or Stone Mountain, or one of those. Based on the height difference, there's going to be a different amount of atmosphere on top, and that's going to change the height of the barometer. And that can tell me what the pressure is for that. In addition to the idea of just height being different, there are also weather patterns that change it. And so you'll see discussions like, okay, I don't know, I might be dating myself. I have no idea. I don't know if you watch a Weather Channel program ever anymore, but like they'll talk about low pressure versus high pressure systems. And so based on as the weather happens, different air fronts will come in and there'll be more or less pressure. And so this will also change it from that, not just height. Now, sorry, too fast. There's another way to measure these, and that's with a tool called a manometer. So for a manometer, it's set up the same way for the most part as a barometer, but my goal is not to compare it to atmospheric pressure. Only in this case. So a barometer is measuring just atmospheric pressure or pressure in a particular space. What we do with a manometer is you set up something called a U-tube. So the idea behind this U-tube is it's filled with a liquid, maybe mercury, maybe something else. And so what happens is one end is going to be closed to vacuum. So we've got this, I'm going to talk about the open-ended version. So the open-ended version, I've got the atmosphere on top. So the atmosphere is pushing down on one end of the U-tube. I hook a gas container up to the other, and it's going to have a gas inside that has some pressure that might not be the same as the atmosphere. Then if I open this, if I've got this valve here open, then I can compare, if I open this, which is what they do on the right side here, I can compare the gas inside this container to the atmospheric pressure. So if the gas in the container is higher pressure, I expect the tube to rise towards the side over here, like this part here. I expect it to rise up so it is higher than that gas because the gas in the container can push down harder than the atmosphere does, so the mercury starts going up. That difference tells us what the pressure difference is. So if the atmosphere is one atmosphere, let's say 760 millimeters of mercury, because let's say I'm right at one atmosphere, and then the difference is 10 millimeters or 20 millimeters or 50, that difference is how much more the pressure is in that gas container. So I would add it. So like if it were a difference of 50 millimeters, I would take 760 plus 50, it would be 810. The reverse would also be true. Let's say the gas inside that flask is actually lower pressure. Then it's going to go the other direction. The mercury is going to, or whatever liquid's in there, I'm just treating it like mercury for the purpose of this, is going to raise up, and now it's going to be closer to the gas side. So it would look something like this. So I've got I'm not going to draw a very good manometer. Textbook authors, there's a reason they pay them to paint things and stuff, make pictures. I'm not very good at it, but it'll get the point across. Let's try this. Dr. Leslie will promise you he will not he'll not try to sell you a manometer based on his drawing. It would not be very good. So let's say this is lower than P atmosphere. So it's a lower pressure thing. What's going to happen then is the level over here will be higher than the level on the atmosphere side because this is P atmosphere. And so now the difference goes the other way. And so now we would subtract from atmospheric pressure to figure out what's inside that flask. So if it were 40 millimeters different, it would now be 720 millimeters of mercury, assuming P atmosphere is 760, because it would be that minus that. So we can use that to figure that out. And so that can tell us what our pressure is. We can compare something in a closed container to the atmospheric pressure, and we can compare those two that way. That's a way of doing that measurement. And so you could take a manometer picture and tell me which side has a higher pressure. And if we gave you the height difference and told you the atmospheric pressure, you could also figure out what the exact pressure is from that. Now, so I'll do this slide and then I'm going to split up in another video for the next part. But when we're working with gases, so there are a bunch of different types of gases, right? Like I talked about, I'm breathing in oxygen. There's nitrogen in the air. We've got a whole bunch of different types of things of gases. We just have a bunch listed here. Things like argon or helium or carbon dioxide or water can be a gas. Not always. Water can also be a liquid or a solid, but it can be a gas. What's important is all these different gases have a number of different properties. And there are 4 that we're going to talk about a lot in this class. We're going to talk about volume. It tends to be measured in liters, but you can measure it in other units. Amount, how much of it do I have? This will usually be measured in moles. Temperature, how much energy does the average molecule have? And that's related to the speed of the molecules. That'll be measured in Kelvin, is the unit we'll be using. And then pressure, often measured in atmospheres. Note that I mentioned this is in Kelvin. I want to real quickly review how to convert from Celsius to Kelvin as a reminder. So our temperature in Celsius, degrees Celsius, is equal to our temperature in Kelvin plus 273. And depending on how accurate you need to be, you can use that 273 or, let me fix that, or 273.15. And depending on the number of significant figures which you have can make sense. So that's a minus sign. Ooh, that was a boo-boo. So I was doing it for the temperature in Kelvin is equal to temperature degrees Celsius plus 273.15. There we go. That's more right. So for example, if I knew something was at 25.0 degrees Celsius, I could plug it into this equation here and tell you that the temperature in Kelvin would be equal to, 298.15 Kelvin. So you should be able to go back and forth between them. Note that in problems we're working with, we'll need to use this in Kelvin, that you will get very weird answers if you answer in Celsius. That'll be a fair bit off. So make sure that you're doing it in the correct unit when doing that. That one comes up a fair bit. We tend to measure things in Celsius, but the equations we're using have to have it in Kelvin. So that goes over sort of the basics of gases. And in our next video, we'll start looking at the different properties of gases and how you can change them and what changes when you try to make a change to different gases.